The cheetah is nature's most iconic sprinter. Built for pure acceleration, it can go from 0 to 60 miles per hour in just 3 seconds, faster than most sports cars. With a lightweight frame, flexible spine, and powerful muscles, it dominates the African plains as the undisputed speed champion of the animal kingdom. But what if we took the cheetah far from its home on Earth? What if we placed it in a space station? Or on the surface of the moon? What would happen to the fastest animal on Earth in a place where gravity doesn't behave the way we're used to? Would a cheetah still be fast without Earth's gravity? To explore this question, we need to understand what makes a cheetah fast in the first place. On Earth, a cheetah's speed is the result of several key adaptations. It has long, slender legs that act like springs. Its flexible spine works like a coiled whip, stretching and contracting to lengthen its stride. Its large nostrils and lungs help it take in massive amounts of oxygen during high-speed chases. And its claws are semi-retractable, giving it grip like cleats on a track. All of this works together to create a perfect balance of traction, timing, and power. But it all assumes one thing: Earth's gravity. On Earth, gravity pulls downward at a force of 9.8 meters per second squared. It gives the cheetah weight, keeps its paws pressed against the ground, and allows it to generate traction with each step. Without gravity, or even with reduced gravity, everything changes. In microgravity, like on the International Space Station, objects are in a constant state of free fall. Astronauts float because there's no solid ground beneath them to push against. In that environment, running is impossible. There's no friction. No traction. No way to push off the ground and gain speed in the traditional sense. If a cheetah were placed in a space station, it wouldn't be able to sprint at all. Its paws would flail in mid-air, its muscles pushing against nothing. Even the slightest movement might send it spinning slowly through the air, unable to control its direction. Speed in this environment is not measured by running, but by momentum. And the cheetah's body, evolved for explosive motion on solid terrain, would be completely out of its element. Now, let's shift the scene to the surface of the moon, where gravity is still present, but much weaker. On the moon, gravity is just 1/6 of what it is on Earth. This means the cheetah would weigh significantly less. A 110-pound cheetah on Earth would weigh just over 18 pounds on the moon. At first, this seems like a big advantage. Less weight means less effort to move. So would that make the cheetah faster? Not necessarily. Because while weight decreases, mass stays the same. The cheetah's body still has the same inertia, it still takes force to accelerate and decelerate. But with less gravitational pull, it has less traction. Its claws can't grip the ground the same way. Each stride could launch it much higher into the air than intended, creating an awkward bounding motion rather than a smooth, fast sprint. In fact, on the moon, a cheetah might find itself leaping in long, slow arcs, spending more time in the air than in contact with the ground. This would slow it down dramatically. Its explosive power would be wasted in vertical motion rather than forward thrust. And when it lands, it would have to stabilize itself again, costing time and energy. This isn't just theory. Astronauts on the moon had to adopt a bouncing, hopping gait because walking normally wasn't possible. Their boots would leave the ground with each step, even when taking slow strides. The same would happen to a cheetah. Despite its incredible strength and coordination, it would struggle to adapt to the weak lunar gravity. So, ironically, the fastest land animal on Earth would move slower on the moon. Now, what about Mars? Gravity on Mars is about 38% that of Earth, stronger than the moon, but still much weaker than what cheetahs are built for. On Mars, a cheetah would still face the same problems: reduced traction, altered balance, and elongated time in the air. It might be able to run, sort of, but its strides would be inefficient and unstable. Speed would suffer. And its body, so finely tuned for Earth, would be working against itself. But here's where it gets fascinating. What if we could genetically engineer or retrain cheetahs for lower gravity? What if we raised them in lunar-like environments, teaching them to adapt from birth? Could we develop a version of the cheetah that thrives on other worlds? Perhaps. Its body would evolve to prioritize control over raw speed. It might develop shorter limbs, stronger stabilizing muscles, or a longer tail for better balance in slow-motion bounds. It might even change the way it hunts, relying more on ambush tactics and aerial jumps than fast sprints. This raises bigger questions. How do animals adapt to alien worlds? Could future generations of life evolve separately on different planets, shaped by gravity itself? And how would we as humans interact with those creatures, if we ever colonize those planets ourselves? The cheetah, in many ways, is the ultimate earthbound athlete. Its design is specific to our planet's physics. Change the rules, and the design no longer works. But that doesn't make the cheetah weak. It makes it a reflection of Earth's unique balance, a symbol of how beautifully nature can sculpt a creature to dominate its environment. So, would a cheetah still be fast without Earth's gravity? No. Its speed is inseparable from the planet it evolved on. In space or on the moon, it would float, stumble, or bounce. It would be out of place. Out of sync. But that doesn't diminish what it is. It only highlights how remarkable our world is, and how every animal, every motion, every moment is perfectly tuned to the gravity we take for granted.